aquatic species. We have fish in these rivers. We have ducks. We have like birds that are flying between different water bodies. So, and then there's two big effects here. One is we don't want to have toxics in there. We don't want to have chemicals that are just going to kill the fish directly or kill birds, like a bird's going to land there. This is a big one in California, selenium in the lake. So there's like this levels of selenium. The birds land there. They drink some water out of the lake and they're dying just from the levels of selenium. But much more importantly and much more broadly are nutrient effects. And I'll talk about this more, where our impact is by putting things that load up the water bodies with nutrients, and too much grows there, and it kills off the water quality by putting too much nutrients into water bodies. So what are the pollutants that we regulate? There's a lot of different, in water and in air. It's helpful to think about what are the different pollutants, because it makes us think about what are different ways we can get at them, what are the different sources, what are the things we're measuring. So we could say there's a set of biological pollutants to water bodies, pathogens, things that make us sick. These are the main ones that we're measuring: E. coli and Enterococci. Enterococci is an indicator organism that shows whether there's human waste in a water body. Enterococci are microbes that live in our gut that we can measure out there in the environment and see if basically there's untreated human waste, fecal contamination in a water body. And this is what our swimming standards are based on. We have cheap and affordable testing that we can do in multiple places. We can go to beaches and say, all right, is the we have a schedule that the EPA publishes of how many Enterococci are safe for us to swim in. Would you let your kids swim in the Mississippi River at, in front of St. Louis? And what's the Enterococci level there? We also have a lot of chemical pollution. We would call this inorganic. This could change the pH of the area. These could be heavy metals. This could be PCBs in the case of New Bedford Harbor Superfund site. Industrial waste. So that would be inorganic, would be chemicals. The organics are the PCBs. Solvents, industrial cleaners, insecticides, pharmaceuticals. And we have so many different ones of these, and it's an expanding list. And there's only certain, for some of you who are in like toxicology, our ability to measure these in the environment is changing over time. So there's a lot of these organic chemicals that we haven't tested for, that we're learning to test for, that we don't know the epidemiology of how it affects people or the aquatic ecosystem, and we're learning more and more over time. So a lot of these are really changing over time in terms of like, there used to be certain pesticides that contaminate rivers. Now there's antibiotics, there's human pharmaceuticals in our water bodies, and it's changing what we're measuring over time. Really, really big ones that cause huge amounts of pollution are nitrogen and phosphorus, coming from agriculture or even just coming from municipal wastewater. These are the ones that cause the aquatic ecosystem to go out of whack and grow too much. They're like, it's putting too much food in the fish tank and it's turning all green. We also have other pollutants that are just sediments themselves, total suspended solids, so just too much particulates going in water bodies. And then we have temperature. You can change the temperature. Power plants, dams, cities can change temperature. That's going to change the aquatic ecosystem. So the EPA has a pretty broad different types of mandates. They're starting with, what we think about first is like biology and human health, but then from there's a whole bunch of different pollutants to be tracking, measuring. Different types of sources have different types of pollutants. So, and then we have where are we going to measure pollutants? Where are we going to measure sort of like water quality standards? So for some of these inorganic chemicals, it could be hundreds of miles downstream that they're accumulating in some sort of aquatic species that might be on the bottom of the river, accumulating over time. It might not be right at the place where the pipe is coming out of the city or the factory. Sediments are really big, so a lot of harbors, rivers, where like there's a mud at the bottom of the harbor or the river, and that's where these organic chemicals and heavy metals are accumulating. You go to the beach, you take a beach measurement right at the level of the water where it's coming in. That's not where the inorganic or the heavy metals are. They're like down at the bottom of San Francisco Bay. We have bioaccumulation, which was big story of pesticides, where it wasn't hurting the smaller organisms. It was like the condors or the eagles up at the top of the food chain where we saw the effects. And then we have things where pollutants go out. The Mississippi River is pretty polluted, but where the Mississippi River goes into the Gulf of Mexico, a huge dead zone, a dead aquatic area where there's no life, and that's related to pollution hundreds of miles upstream in the Mississippi River. We have it in the Great Lakes, big dead zones that happen in the Great Lakes. So there's a lot of pollution happening up on the Ohio River, but the Ohio River's gurgling out into the Great Lakes, and then there's a big dead zone where all the fish are dead in the Great Lakes. Important here is it's interesting. There's different. Nitrogen is a limiting nutrient in saltwater, but phosphorus is a limiting nutrient in freshwater. So limiting nutrient meaning as you add tons and tons of nitrogen in your runoff or in your sewage treatment outfall, you can have huge increases in algae growth, and that can be affected differently by the different, and I'll talk some more about those, where that comes with regulation. But we have point source pollution and non-point source pollution, as I started to motivate. So point source pollution is where we have a pipe and outfall, and the EPA has what's called a pollution discharge elimination system, where each pipe that's emitting can have, like a factory or industrial space, will have a permit for how much they can emit out of that pipe. The interesting thing in water quality is a lot of times it's not just the private sector. It's sewage treatment plants are owned by municipal governments or some sort of, like East Bay Mud, it's like in between government, public and private. Another one that's come up recently, so agriculture, for political reasons, is exempted from the Clean Water Act. Agriculture being a huge emitter, but recently we have what's called CAFOs, big animal feedlots, and these are sources of huge amounts of water pollution. A big chicken warehouse, big pig warehouses, big dairies where just thousands of animals are packed in there. And they, because they're a specific point source, and they might have a pipe going out to a river or emitting from a single place, they can be required to have these discharge permits. Oil and gas production have been removed from some of the Clean Water Act as well because of their political savvy. I'm realizing that I forgot to turn off. Okay. So the previous approach with water quality when the Clean Water Act started was looking at water quality of different bodies of water. Different bodies of water receiving pollution had different characteristics, how much it would get diluted, what type of mixing there was, what type of sort of retention times there were. Currently, the EPA is moving towards an approach that's based on technology, what's called the best available technology, BAT. So they're creating national standards saying what's the best technology available for treating the water that you release, and within that, they consider sort of the engineering possibilities and the costs of doing that. So the EPA says if you want to pollute from, you want to emit to the river from your sewage treatment plant, here's the best available technology for sewage treatment plants for reducing this pollution. So we want you to show that you have in place the best available technology that has some sort of embedded engineering issues and marginal cost issues in it. So this is the just a look at some of the wording from the EPA. Effluent limitations for categories and classes of point sources which will require application of the best available technology economically achievable for such category. So limiting pollutants by saying what the best technology there is, and then in the government regulation, factors regulating the assessment of best available technology should require these engineering things and the cost of achieving such effluent reduction. So implicit in their evaluating what's best available technology is they're also evaluating cost, which is important for us as economists thinking about what we're going to require people to do. We want to require people to do things that has some cost effectiveness in it. So the big story of wastewater treatment over time, since the 70s, $85 billion has been spent in grants from the federal government. The federal government would give 75% of the capital cost of building these plants. Huge amounts of energy and infrastructure. So it's up to 3% of the electricity consumption in the United States is going to wastewater treatment plants. So they built plants that were huge industrial processes. Often, this is reducing now, but for a while, it was up to 30% of the budget of the EPA was giving out these grants. So this is a huge arm of the EPA, is just managing grants to different municipalities to upgrade sewage treatment plants or build sewage treatment plants where there weren't anymore. Let's think in 1972, there was very little sewage treatment. And so this was building sewage treatment plants for cities across the United States. In the United States government budget, there's the Defense Department, the biggest expenditure of all. Second was building the interstate highways, and third was building these sewage treatment plants. So a huge scale in terms of what the federal government has invested money in. One point that we're at now is when you create this huge subsidy coming from the federal government, it steers what kind of technology gets implemented. So very industrial, very electricity heavy, very huge amounts of concrete, very centralized. So instead of getting municipalities to search for the most effective and efficient ways to clean up water, we told them what to do and we bought it for them. So accumulating over 40 years, this technology is very energy intensive and very capital cost intensive. Now that the government is reducing how much it's going to pay for this, we need to innovate in other directions that are going to have less energy. And now that we want to think about reducing our energy footprint, we have these sewage treatment plants that have a huge energy footprint. So then we have non-point source pollution. This is a much more difficult thing to regulate. And this is a difficult thing to regulate in the United States where we're not putting regulations on agriculture. Agriculture has maneuvered that they're not going to be affected by the EPA. There's a huge amount that we have in cities to deal with urban water runoff. So there's rain, and rain doesn't go into our sewer system. Rain goes into our storm drain system. If it rains right here, it goes into Strawberry Creek. In Berkeley, the creeks are the storm drain system. So, but coming off of cities, there's a whole bunch of different pollution that can drain off of cities into storm drains. And are we going to build systems to cover urban water runoff, to either capture it or clean it on its way out to the bay? So it wasn't regulated, just sewage was regulated, but now municipalities are having the non-point source pollution from their runoff regulated. There's discharge permits. There's measurement of what's coming out of their storm drains. So the storm drains from Berkeley, they're now measuring how much nutrients that's putting into the bay. The way they regulate this is this term, the total maximum daily load. So this is for a lake, for a river, for some receiving water body, what's the total amount of nutrients that this source can take safely without upsetting the aquatic system? What's the total amount of nutrients? And then they have it per day, and then they have finding what the different sources are. So this is sort of a newer approach, the maximum daily load. And in watershed management, it's sort of time to face up to agriculture because in a lot of areas, sort of in the middle of the country, huge amounts are coming from agriculture, and what's their sort of allowable load that they can pollute. So here's just some graphs thinking about non-point source pollution and how big it is. This is estuaries, lakes, and rivers. So the purple being non-point source pollution. So this light blue here, this is combined sewer overflow. So when it rains a lot, water goes into sewers. Sewers are allowed to overflow a little bit when there's a high rain event. So the light blue, the second biggest chunk. And then there's industries and natural causes with smaller chunks. But this non-point source pollution is a huge thing to try and regulate going forward. As I tried to say before, nutrients are the pollutants. Nitrogen and phosphorus are the pollutants. So it's not just, it's not pollution where we think of there's a toxic green sludge going out into the river. There's dissolved in the water, there's nutrients that when it gets to the river, it leads to a huge amount of algae growth. It's a little backwards because you're like, oh, the river is growing too much biologically. It's not like we've killed it, it's growing too little. What happens is you have huge algae blooms, so a river will turn all green with algae. Those algae will die and sink down where they get decomposed by a layer of bacteria. And those bacteria that are decomposing the algae use up all the oxygen. So in any water body naturally, there's a whole bunch of dissolved oxygen. That's how fish can live. They're going through and they're taking dissolved oxygen out of the water. When there's one of these huge algae blooms and then decompositions, there is no oxygen dissolved in the water anymore. And that's why all the fish would die. We have the term, that's the big term in water quality, biochemical oxygen demand, the BOD level. Total maximum daily load we could measure in BOD. I'm going to leave it to you guys in environmental science to understand it more than that, but the BOD level is something that we can measure. It's our policy, the thing we're trying to change in policy. So I'll go through an illustrative example for Boston Harbor. I'm from Boston, so I'm going to make you leave California briefly. Usually I'll stick to California examples, but this is a huge example. Boston was not dealing with cleaning up the Charles River, the main river that goes through the city, or and a group. So there's Massachusetts River Water Resource Authority. So Boston has many small towns. It's not just one big metropolitan area. Many small towns along the Charles River and surrounding Boston. So you create a regional water authority that can go across the legal stratus of each town. And then there's a nonprofit group, the Charles River Conservancy Association. And they are a nonprofit group, concerned citizens. The river in our town is polluted. We can't swim in it. We can't recreate in it. There's no fish in it. And they sue at the federal level. They say Boston is not living up to what it's supposed to under the Clean Water Act. The EPA gets involved, and a $4 billion sewage treatment plant is built in the middle of Boston Harbor. Super state of the art. If you ever fly to Boston, it's right next to the airport, and you see these weird egg-shaped things that are the digesters. You can see them really close from the airplane. It's out in the middle of the harbor. So sewers are upgraded to carry all the water out there to this huge plant. Lots of electricity, lots of natural gas, super energy intensive, and then it's sent out into the ocean. But it's worked. It's cleaned up. It's totally been effective over time. So this is a map of where the pollution was out into the harbor, and then up there, that hook at the top is the Charles River. So Deer Island Sewage Treatment Plant goes online. This is the 80s, early 90s, 1999, 2007. The water quality goes cleaner and cleaner and cleaner up the Charles River. Whole bunch of different things they had to do this besides building a sewage treatment plant. Here is the swimmability. So just as I said, what are we measuring? What do we want this to be, right? So this is a swimmability standard. Colonies of enterococci in a sample. So taking a water sample, how many colonies of enterococci do we find in a sample? This is what is the swimmable standard, less than a certain number of colonies. So a biological measurement, and that we're mapping, we're showing that we're moving it back upstream inland. Basically, there's leaky sewers all over the place. Every city is full of leaky sewers. This city is like 300 years old, right? So people were building pipes out of wood, then pipes out of ceramic. They're cracked sewers all over the place. So we can build, a flashy $4 billion sewage treatment plant, but we also have to track down and go under buildings and under bridges and all sorts of places to find all the sewers and, sort of track down places where they're all being emitted. Here's, the point source, the point source permit for pollution. So they're measuring at the source, and this is kind of boring data. It's just showing that the sewage treatment plant is working. Like here's the federal standard for the pollution permit, and this is the biological oxygen demand that I tried to talk about, the amount of proxy for the amount of nutrients that we're putting into the water. And it's, it's working. The sewage treatment plant as designed is working. We're just showing that one is suspended solids, total suspended solids. EPA regulation for biological oxygen demand 25 in their TPDES. There's a whole bunch of other things you have to track down. If you want to look at heavy metals or inorganics, the sort of things that we think of like the green goo type of pollution, you actually have to go through that a different way. These sewage treatment plants can take some of that out into the sludge, but here's for metals. So these things are like toxic in a completely different way than this biological demand. A lot of these, so obviously this has worked, the huge reduction in the amount of metals being polluted into Boston Harbor. The way you go after these things is going upstream, finding the sources, finding what's going into sewers, going to plants, industrial plants upstream and trapping it there. So in order to reduce metals, you have to go upstream to find the sources. They also, will catch these in the sludge that comes out of the sewage treatment plant and have ways to process these out of the sludge. They used to just, dump the sludge straight into Boston Harbor. Now they have ways to process it and go put it somewhere else. Organic pollutants are very interesting, and this is what I was talking about, where we have new ways of measuring these things at really trace levels. Here we have volatile organics, pesticides, phthalates, phenols. I'm not really knowledgeable about toxicology, but we're getting increasing information that these things are all around us. Endocrine disruptors, they're called broadly, like as a class of things. Things that mimic estrogen in our bodies. They can measure them in our blood. Everybody's blood seems to be showing up with trace amounts of these chemicals. There's also antibiotics that are used, or different pharmaceuticals that are used, that you can measure in sort of pollutant discharges. They make it through the sewage treatment plant, and then they get emitted into the environment. You go to some rivers in the Midwest, and you can find different chemicals that people are taking. They're going straight through the people, and they're going out into the... So this is a whole bunch of tough things to measure and tough things to find. We have been able to reduce them. There's obviously better sewage treatment plants, and more is getting used up. But the science on these sort of things is still evolving, right? There's classes of pesticides we can say, okay, they're bad, we have to remove them. But we have what's these more friendly pesticides that are more related to endocrine disruptors, but they have sort of more mysterious pathways. And here we have to do more epidemiology. We have to do more about how to trace it. We have to do more about how to remove it. We don't, this is like still evolving in knowing how to do it. So one of the big questions is, can you swim in the Charles River, right? I mean, the EPA is using swimmability as a proxy for human contact, as a proxy for, is it safe? But you have this real question is, are people going to, there's this beautiful river going through this hot, muggy city, are people going to start swimming in this river? So these graphs are showing upstream, middle, and downstream, the levels of pollution. So the answer is, you can swim if it's not been raining. And this happens a lot of places with water quality, right? If it hasn't rained in the last day or two, it's safe to swim. That's because when it rains, we have this thing with stormwater. Stormwater is going to pulse out leaky sewers, dog poo, oil, motor oil, a whole bunch of things from our city is going to get pulsed out with rain and runoff. But if it hasn't been raining for a couple days, it is actually safe to swim in the Charles River. 2 days after rain, and you should be good to go. What's that? I have not swum in the Charles River. I'm from a town north of Boston where it's been cleaned up longer, but there is a place where the sewage outfall from Boston used to come out, closer to where our beaches were. And the fact that there's now a giant sewage treatment plant between that outfall and not is a huge difference. But no, where I would go is on the open ocean, and the open ocean there just has such a tidal effect that the ocean is able to clean things very quickly. So one thing that's really been interesting and sort of like, a follow-up, a side thing that has happened is when you clean up your leaky sewers and you improve your sewerage, so there's towns way up in the Charles River, up high, now 100, they're pulling the groundwater out of the ground, using it in your municipal system, and then they're sending it all out to sea through the sewage treatment plant. So there's less and less water going into the river from these upstream communities. So if it doesn't rain in July or August, these cities, this area of the river is not putting any fresh water into the river. So there's been big algae problems where there's not enough fresh water going in. So like one solution would be like, is there some way to treat some of the water locally so that the towns upstream can be putting some of the fresh water in? A lot of the way water quality works is through dilution, right? Always just put more water into the system, it will reduce your overall levels. So in some of these upstream communities where there's been algae blooms or concentrated pollutants when there's no rain, they're trying to figure out what ways that we can, that our community can be putting some of our water into it. This is sort of that thing of like, they fixed the sewers and then they created another problem because